Hello everybody. So let's look at this problem which involves something called the first derivative test. So the statement of the question as I see it from the assignment is that we're given a function or a curve, however you want to think about it, and we want to find out where it's increasing and decreasing and if it has any local extreme values such as a maximum or a minimum. Okay, so the way that we would do that is through all of this. Okay, so we can tell if a function or a curve is increasing or decreasing based on whether the derivative is positive or negative. Okay, so the derivative slope of the curve, so if the slope was positive, it would be going up from left to right, and if the slope was negative, it would be going down from left to right. So that's where that comes from. As far as figuring out if there are any points that are local maximums or minimums, it all depends on how the derivative changes signs at critical points. Okay. All right. Now you can see the thinking right here if you want to read it, but I'll just go ahead and work the problem and explain it along the way. Okay. All right. Now I see my answers are given. Okay. I can refer back to this in a minute. Let's talk about how you solve it. All right. So statement of the question. I have this curve, x to the 1/5 power times x plus 30. Where and if is it increasing or decreasing? Doesn't have to be both or either, all right? And are there any local extreme values, maximums, and minimums? So breaking into steps, here's how I would do it. Step one, I need to know what the derivative is because everything I want to know can be found that way. It can be found through analyzing the derivative. So I'll need to find the derivative. The way I'll do it is I'll take the function as it was given. I'll distribute the x to the 1/5 power like so. And I do that just to avoid having to use the product rule. It seems simpler that way to me. Okay. Now, if I take this and use this rule, then I get this derivative, 6x to the 1/5 over 5 plus 6 divided by x to the 4/5 power. Okay, so there's my derivative. What I do will be based on analyzing that. Now, you may notice that in this information here, we need to know critical numbers to fully evaluate this. Okay, so I'll locate the critical points or the critical numbers. Now, a critical point or a critical number is any point where the derivative is either 0 or undefined. So let's explore that. So I'll do in step 2, step 2a and 2b respectively. So my first thought is where's the derivative 0? So okay, right here I've taken the derivative that I found right there and I set it equal to 0 and I see if I can solve it because that would be an answer to the question where is the derivative 0? So I'll do this. I'll move this term to the right hand side. It becomes negative. Then I'll multiply both sides by x to the 4/5 power to cancel that fraction. On the right hand side when I do that, I'll get x to the 1/5 times x to the 4/5, and from there when you multiply like bases you add the exponent, so I'll just get x. Okay, then I'll multiply by 5 and divide by 6 simultaneously. I'll get x is -5. Okay, so that's my first critical point. The derivative is 0 if x is -5. Now what about the other case? A critical number or a critical point could be a point or is a point where the derivative is 0 or undefined. Okay, so the other possibility is that the derivative might be undefined. So here again is the derivative. Think about what it would take for this to be undefined. I mean, this is just a mathematical operation. We take a number. We take the 5th root of it. We multiply by 6. We divide by 5. Then we add. We take our number. 5th root, then 4th power, and then divide 6 by that. And that's your answer. It's just a sequence of calculations. What would it take for that sequence of calculations, that formula, to be undefined? It would be undefined if we were dividing by 0. I don't see dividing by 0 being a possibility here because I just have 5. But the x there, or the x to the 4/5, would make this expression undefined if it was 0. To solve that is to take 0 to the 5/4 power and you'll get 0. So this is undefined if x is 0 because you'll be dividing by 0 in that case. So here are my critical points. One of them is -5, and which causes the derivative to be 0, and the other one is 0, which causes the derivative to be undefined. So now I know my critical points. Now notice in my procedure in this information, we can figure out if there's a local minimum or maximum based on the derivative changing signs at a critical number. So I have my critical numbers. So the way I do this is I just make a chart of the critical numbers, imagining the x-axis, and what the derivative does, imagining the x-axis. Okay, so I'll just say that what I could describe that as I'll test the derivative as being either positive or negative outside of and in between the critical numbers, and I'll just make a chart to summarize what I find. So here's what I know so far. At 0, at x is 0, the derivative is undefined. I put UND. At x is -5, the derivative is 0. Now, what are the other possibilities? At every other spot, it must be either positive or negative. So what I do is I can take numbers outside of and in between the critical numbers, put them into the derivative, see what I get in terms of it being positive or negative. Now, the derivative can't change sign without passing through either a 0 or an undefined. So you just have to take one point in each spot and test it. You can take any point you want. So like I need to take something left of -5. I happen to take -32 because -32 was a perfect fifth root and I could work it out on paper. You don't have to do it that way. Take a number left of -5, put it in the derivative, see what you get, and make a statement if it's a positive or negative. Okay? All right. So I got a negative real. I got -81/40. You can do it however you want. Take a number left of -5, see what you get. So I put a negative right there. Then next I took -1. -1's between -5 and 0. I put it in my function. I got 24/5. That's a positive number. So I put a plus on my chart. Then I needed a number right of 0. I took 1. I got 36/5. That's positive. So I put a plus. So there's your chart. There's your information. Now I'll interpret it. Okay, so first of all, let's do two things. Question initially said, where is the function increasing or decreasing, and are there any local maximum or minimum points? So decreasing means the derivative is negative, so that'd be -infinity to -5. This portion of the curve. If you were to scan the x-axis from -infinity to -5, you would see the curve is falling from left to right. We also say it would be decreasing. And then it's increasing wherever the derivative is positive. So that's this portion from -5 to 0 expressed as an interval right there, and then from 0 to infinity expressed as an interval right there. So that's where it's increasing and decreasing. My test values and incorporating that information on the chart tells me. What about local minimums and maximums? Okay, now if I refer back to that thing over there called the first derivative test, I'll have a local minimum at a critical point if the derivative transitions to being negative to positive. So from negative to positive. Why is that? Well, think of the curve as falling and rising like that. So the curve is falling, and then I get a point where I have a critical number, and then it rises on the other side. So that would be a low spot, or what we call a local minimum. So that's at the spot where x is -5. If I try to find the y coordinate, I'll have to put that in my function f of x. Remember, f of x, this tells me points on the curve. The derivative tells me critical numbers and whether the curve's rising or falling. If I now want to tell you there's a point on the curve that is a local minimum, that the curve dips down to that point, to tell you what that point is, I would have to take the x coordinate and plug it in. So this is the equation for that original curve. Putting -5 in, I'll get -5 to the 1/5 power times -5 plus 30. That's 25 times the fifth root of negative 5. I can take out the fifth root of that negative 1 right there as negative 1. I'll get negative 25 times the fifth root of 5. Okay, so that's a local minimum. Now this curve wouldn't have a local maximum. Why is that? Well, to have a local maximum, the curve would have to rise and then fall. So there would have to be some critical number that had a positive derivative on its left and a negative on its right, but there isn't one, okay? There's no portion of this curve where it's rising and then falling. So it doesn't have a local maximum. Now that's what this test says, okay? If you read it, that's exactly what it says. All right, so I interpret it that way, and here's my answer. Okay, so that's how you solve it. Now there are a few other things I want to say. I think it's a little bit unusual how the answer was expressed here. So see how it says the function is increasing from negative 5 to infinity? I think it'd be more typical for people to break that up, because it's increasing from negative 5 to 0, and then there's something else happening, a critical number, the derivative's undefined, and then it picks up from there and continues to increase from 0 to infinity. But that's combined as one single interval right there, or so right here. Sorry, no, right here. Increasing from negative 5 to infinity. Okay, so it's expressed as one interval, whereas I broke it up as two as I solved it. All right, now additionally, I wanted to talk about what's going on here. See this critical number, this critical point where the derivative's undefined? So I made a video already about all the possibilities that we could see if the derivative was undefined. So if we had a critical number, it was the type of critical number where the derivative's undefined. I wanted to talk a little bit about what that could mean. What we have here is a vertical tangent on the problem we're doing, because the curve rises, but then there's a spot where the derivative is undefined, and then it continues to rise. On a cusp, it would be falling and rising. And on a corner, you would have these lines, all right? And if it was not continuous, you'd have missing points or jumps on the curve, okay? So I would like to see, is there some corroboration of that? That the curve is falling down to a local minimum, then rising, passing through a vertical tangent, and then continuing to rise. I'd like to see that, okay? I've worked out all the math, and what we're doing here is trying to determine things about the curve without seeing it, just based on what the derivative does. But now that we're done, it would be nice to see it, because maybe we're learning this, and it's nice to see confirmation of what we do. So I'm going to open this. Okay, so here I've graphed it, and I think I see exactly what I was saying. The curve's falling down to a low point right here, a local minimum, which happens at x being negative 5. That's where we found that point to be. But then it begins to rise, and I notice at 0, our other critical point, it looks straight up and down there. It looks vertical, and then continues to rise from there. So I don't, when I worked it, I didn't imagine that shape exactly, but this is more or less what I thought, and it's entirely consistent, totally 100% consistent with this chart right here, okay? All right, so that's how we do it. That's called, that whole procedure, I guess most specifically through steps 3 to 4 is called the first derivative test. So you can solve other problems the same way. The only difference might be that the derivative be a little bit different. Maybe the algebra solving for the critical numbers be a little bit different. But the first derivative test itself of the test values, the chart, and the interpretation, that would be the same in each case.